The topic for today's talk is severe weather. And at first glance, when you see that title, you may wonder what that has to do with physics. Well, it turns out that meteorology, which is the physics of the atmosphere, addresses a lot of these topics. And I think that what you'll see as we go through this is that there is a physical basis for a number of facets of meteorology. And in fact, the weather is one of the most pervasive manifestations of physics that we have around us. Now, I've listed in the first page of your note packet the main types of severe weather that affect this part of the country, and I'll be dealing mainly with the first three today. We don't have time to go through all the items on the list, but we'll go through some winter storm examples, some hurricane examples, and some thunderstorm and tornado examples. And in the case of all of these severe weather events, there are several factors that determine the magnitude and types of impacts. We've listed those here. The first one is the obvious one, the severity of the event and where it occurs. But the impacts are also determined to some extent by the infrastructure that is affected by the severe weather event. And as far as people go, the impact is determined by their level of preparedness, the time they have to get ready for the event. And what I'll try to show as we go through these different topics is that our stage of technological development has a lot to do with these impacts by first giving us our infrastructure, what can be affected by severe weather, and as infrastructure develops further, that can make us more vulnerable in one sense to severe weather. It can also be an asset in the sense that we have more options for shelter. But the preparedness aspect of the technology is the one I'll emphasize the most. And what I'll try to show is that we are indeed far more prepared for severe weather events in general now than we were at other times over the last 100 years. I'll start with just a quick review of some of the major milestones in atmospheric science. And in many respects, these advances are tied in with advances in physics. Before the 1600s, we didn't even have barometers and thermometers to let us put numbers or to get quantitative with the atmosphere. We've had them for about 300 years now, so the longest records we have are about that length. The real impetus for meteorology came along in the 1860s when the telegraph permitted the transmission of weather information in real time. And we'll show you some examples today of where we now stand in the transmission of weather data. In the 1930s, we began our first measurements of upper air weather variables. There's an instrument called the Raywin sonde, which we have an example of that we'll pass around for you. This is an instrument that's attached to a balloon. This is Bill Chapman, who will be running some of the controls up here. He's getting the Raywin sonde started. That package has in it a barometer. You can actually open it up if you pull up on the top half of the cardboard. That box separates into two. In fact, there's a barometer in there. It's an aneroid barometer that measures the pressure. You can give it a good yank. It's been through the wars. It's all right, it can stay apart. There's also a thermistor to measure temperature. There's a little white rod you'll see in there. There's also a humidity measuring instrument. And that was a major advance in the sense that it permitted us to get a three-dimensional picture of the atmosphere. Up until the 30s, we were pretty much confined or stuck with surface variables. Now we could get a three-dimensional picture. And in fact, that led to some of the other items on the list here. Radar came into use in the 1950s, largely as a byproduct of the war effort when radar was used to detect aircraft in the 40s. Computer models came to the fore in the 1950s and 1960s. And in fact, it's those computer models that make use of the upper air data that is retrieved by those Raywin sonde instruments that are launched all around the world several times a day. Satellites came into use in the 1960s for meteorology. We'll see some examples of those. The 1980s brought us Doppler weather radar, which lets us detect rotating thunderstorms that produce tornadoes. I've put down a few of the more recent technological advances. In the 1990s, we're seeing atmospheric profilers, instruments that can retrieve upper air information from the ground. So that Raywin sonde, which is looking like it's seen better days, which it has, is probably going to fall by the wayside as one of the major weather tools in the next 10 or 20 years. We've also seen some automation of weather stations over the last 5 years or so. Now, the three types of weather I'll be going through are these. We'll start with a comparison of two blizzard events, one in the 1880s and one several years ago. And this will let us look at the impact of computer modeling on weather prediction. And you'll see some very striking contrasts in the weather predictions we had for these two systems. We'll then compare two hurricanes, one in 1900, one in 1992. The major tool here will be satellites. You'll see how satellites were used in 1992. They were not around in 1900. We'll compare two tornado events, one in 1925 and one in 1991. The major advance that ties in here is the use of radar for the detection of tornadoes and the severe thunderstorms. But every one of these three techniques or three technological advances that we'll be citing has its roots in physics. And we'll try to point out some of those roots as we go along. We'll start out with the two blizzard events. In your notes packet, we gave you a contrast page where we tried to cite what was available in 1888 for weather forecasters and what was available in 1993. In 1888, about all that the weather forecasters had at their disposal outside of a look out the window and the instruments outside the building was the telegraph. They could receive information from other cities by telegraph, but that was about it. And that telegraph would send them current information or past information, certainly no forecasts. There was no upper air data, so even with the telegraph, they could only get surface information, no computer models, no satellites. The bottom line is that the forecast of this storm in 1888 was rather disastrous. In your notes, I believe we gave you a copy of the official forecast for the day of the blizzard of 1888. Blizzard happened on a Sunday and a Monday. You can see that the forecast here that came out of Washington does not even mention snow for the Northeast. And it was the Northeast, the mid-Atlantic region, that was hit most heavily by this particular blizzard. In your notes, we've summarized some of the features of this storm. It produced the heaviest snows on record at many cities in the Northeast. A few of these records fell by the wayside in the storm 3 years ago and in the one in January, but many of the records still stand. The winds were near hurricane force, 50 to 70 miles an hour. Temperatures were way down. These were genuine blizzard conditions. Snow drifts 30 to 40 feet. And the coldest March day on record in New York City's history occurred during this event. Given you a summary of the scope of the disaster. There were about 400 deaths in this event, largely because there was no adequate warning. We'll show you a little video in a second. You'll see that people set out for work that day on the Monday, assuming that the snow would probably stop since it wasn't forecast. All utilities were knocked out. there were some far-reaching consequences of this storm. This storm was the impetus for putting utilities, the wires in particular, underground in major cities. You'll see in the pictures in just a second, the wires are above ground, and they paid the price. This was also the stimulus for putting the trains in urban areas underground rather than using elevated trains. So we could do video 1. This is about a 1-minute summary in pictures, and there are some words here of what New York City looked like during this 1888 storm.
As in 1993, it was a common mode with many of those technological safety nets which caused most of the deaths. New York returns people to work out of town to live on. Mary Kay was the author of a book called Elizabeth A. She lives and writes in Santa Fe, New Mexico.
The elevator had been going only a few years. And that really revolutionized. People could live in the Bronx or Brooklyn and work. They could commute easily. The New Englanders just did it. Their fathers, grandfathers, way back, had been doing it. They stayed in their houses. They had food in the cellar. And the New Yorkers had this thing about getting to work no matter what. And if their transportation wasn't available, they would walk miles, like 10 miles. There was one man who got stuck on the train as it was headed into Manhattan. So he walked and crawled along the tops of the train to get to Grand Central. He did.
Okay. That'll just give you the flavor of what things were like in New York City. I'm not sure too many of them actually walked 10 miles to get to work. But the fact that the impacts were as severe as they were was due to a combination of two things. One, lifestyles had changed. Commuting was just becoming the standard way of life, as you heard in that clip. The other is that the forecast was so terrible. So you had commuters setting out to work with no idea of what was in store, and the price that was paid was a fairly high toll in injuries and even in deaths. What we want to do is compare that storm with one that occurred 3 years ago last week. This is what they had called the superstorm of the 20th century. We also had another storm that was almost as severe in January of this year, although this one in many respects was the more impressive system meteorologically. This storm tracked up the East Coast. Here's a sketch of the path that the storm followed. It originated down here in the Gulf of Mexico and came up almost parallel to the coast. Now, for this storm, we had satellites to track what was going on in real time. We had radars and we had computers. One of the first signs that this was going to be a significant event is this satellite picture. This is an infrared satellite picture. We'll be seeing the mechanism here in a few more minutes. But this darkly shaded area, it's artificially enhanced, is an area of very strong thunderstorm activity down on the Texas Gulf Coast. What happened here was that these strong thunderstorms formed and released latent heat, the heat of condensation, that heated the atmosphere over a large area, and that caused the air to expand laterally, which meant that down at the surface, they had less air above them after a while. The low pressure started to form. The pressure started to decrease fairly rapidly at that time, and they were on their way to a major event. But this was one of the signs that forecasters used when they realized that this was going to be a major event. There were some earlier indications that we'll look at in a second, but that one was the one that said things are for real. This is what the storm looked like on a weather map. In fact, this picture is one that some meteorologists have had framed and have hung in their offices, in their living rooms in some cases. It's a low-pressure system that dominated the entire eastern part of the country. The low pressure at the time of this map was setting records. Many places had never had a pressure that low before. But what we want to look at is the forecast of this storm. This is how the storm looked when it was in its prime. The low center there is about over New Jersey. With one of the computer models, in fact, several of the computer models around the world, forecasts of this storm started to appear 5 and 6 days in advance. In your note packet, there should be a picture, this picture, showing the forecast from a computer prediction model. This forecast was made 5 days before the storm was at its peak. So this forecast was made 5 days before the Sunday when the storm was in its prime. This is an upper air forecast. Those lines are isobars, lines of constant pressure. What they wanted to look at is the bottom panel. That's the surface weather map forecast. If you look closely at this, there's a very strong low. It was forecast 5 days ahead of time in almost the perfect position. If you get out the magnifying glass, that low is maybe 100 miles offshore when it should be right along the shore. But 5 days before this storm, there was no sign of it. Yet these computer models picked it up and gave excellent forecasts. The result is that the human forecasters were alerting the public to the possibility of a storm like this 4 and 5 days ahead of time. When things did start to explode with those thunderstorms along the coast, the warnings were issued. The result is that the warning time, the time between when winter storm warnings and blizzard warnings were issued and when the conditions set in, the warning time was typically 24 to 48 hours, which means people had plenty of time to prepare for this storm, in contrast to the 1888 event. So what we want to do is take a little trip through computer model forecasting so you can see what these where these computer models come from and how they tie in with physics, keeping in mind that we now have a fairly established and successful system of computer model usage, not just in the US, but in several other countries. We've put in your notes a summary of what these computer models consist of. Now, these models are essentially mathematical formulations of the physical laws that govern a fluid. And the atmosphere is a gas, so it's a fluid. These models consist of several equations. They're conservation equations. There's an equation for wind, which is the conservation of momentum, formulated mathematically. There's an equation for temperature, which is the conservation of energy. Those are conservation equations you run into in physics, either in high school or in college. It should be both. There's an equation for the conservation of moisture. And in each of those equations, you end up with an expression for the rate of change of the weather variable that's on the list. So this model will tell you how each weather variable is supposed to change over time. We have down here what the changes are caused by. Each of these physical processes is built into the model through its formulation. So we have all the processes, or the major ones, that affect temperature, the major processes that affect moisture, which in turn produce the rain and the snow. So they apply these models, or they apply the equations with the actual data on a network of points. And this is an example of the network of points from one of the models of our weather service. So they're essentially solving those mathematical equations at thousands and thousands of points. Every place where you see an intersection of two of those checkerboard lines, those equations are solved. These models typically solve those equations at 20 or 30 levels in the vertical. So there are 20 or 30 times as many points as you see there. And many of the models have these grids, as they're called, covering the whole world. So you quickly get into literally billions of calculations to crank out a forecast for just 24 or 48 hours. That's why these models are run on supercomputers, the fastest computers in the world. In fact, one of the drivers for the development of faster computers has been the weather prediction community. As faster models have become available, the weather forecasters have been able to use these models at finer and finer resolution. You've summarized in your notes some of the other characteristics of these models. One, we'll take a look at two final items on this subject. There's a summary in your note packet of the errors, the relative errors from these computer weather prediction models over the past 40 years or so. And the quantity that's plotted there is essentially the error as a percentage of the real variance that was out there at the time the forecast was for. You can see how the error has gotten smaller and smaller over time. These different lines refer to different models. Presumably the models are getting more sophisticated over time because the errors are decreasing as the next generation of model comes into use. So right now we're down at about this part of the scale, which is saying that our errors are maybe 1/2 to 1/3 of what they were back in the 1950s. So we've come a long way, primarily because of these computer prediction models based on the physical equations for the atmosphere. Progress has not come overnight. It's come in fits and spurts, but the trend is clearly there. So we can take some consolation here in knowing that our forecasts are now much better than they were even 30 or 40 years ago, let alone 100 years ago when we had that blizzard of 1888. Now, we have one example of the computer model forecasts for Champaign. This is for the next 7 days. We just took the output from our Weather Service's computer model off the computer this morning, and you can see for yourselves whether this works out or not. But this is the forecast for Champaign for the high and low temperatures for the next 7 days. Starting with today, and the model says we should get up to 53, 61 tomorrow, high of 46 on Monday. You can see where we're supposed to get colder early next week. Then we warm up towards next weekend. The lows actually drop into the 20s Monday and Tuesday. But you can see how this works out. There's no guarantee it will work out perfectly, but based on past performance, it should be in the right ballpark. Over on the right, there are also the probabilities of precipitation in each 12-hour period as you work down the timeline. This computer model is saying we have a very good chance of rain late tomorrow. In fact, an 85% chance of rain overnight tomorrow, Sunday night into Monday morning. Then the model says we should have a dry day or two and return to some middle-of-the-range conditions later in the week. This is straight out of a computer model. It's untouched by humans, except for pushing the print button. So you can see if this works out. And again, we don't know because that's the next week that we were just looking at. Now, does anyone have questions on the computer models that you want to ask about before we go on to the next topic? Okay, we'll move on then to the second of the three items we had listed, which is the hurricane topic. And the comparison we want to make here is between a hurricane in 1900 that hit Galveston, Texas, and the strongest hurricane the U.S. has had in the last 20 years, which was Hurricane Andrew in 1992. We've put down some of the comparative statistics. Turns out that Andrew was the stronger hurricane. You'll see some footage from the remains of Galveston in 1900 in just a second. This hurricane in 1900 killed 6,000 people. It was the largest, that's the largest death toll the U.S. has ever had from a natural disaster. The storm surge was the main cause of the tragedy in Galveston, but these bottom two lines are the ones we want to focus on. When it came to the guidance, the forecast guidance, all they had in the case of the Galveston storm was one isolated ship report from a couple days earlier. That report came from a ship down near Cuba that reported very strong winds. So there was no warning for this storm. And that's the main reason why the death and injury and the death and injury tolls were as high as they were. In the case of Hurricane Andrew, which we'll look at, we had satellites, radar, and computers feeding into the forecast system. The warnings were quite adequate on this storm. People had more than 24 hours to evacuate coastal areas. We have a short video on the Galveston storm. This lasts about 1 minute. You can see what Galveston looked like. There are still photos only. And it's a fairly grim scene, and they will refer to this absence of warning in the video.
Texas lay in mountains of the thousands of dead were entombed within the rock. In Galveston, Texas, we found out just how terrible a hurricane can be.
I don't think that most people would have had any idea of what was in store, although the situation began to look worse and worse throughout the afternoon. And by late afternoon, I'm pretty sure they were in for a lot of trouble. The program was sent by the meteorologist in Galveston. I was saying that he thought there was going to be a large part of the city underwater.
Winds and waves splintered and broke homes apart. A tremendous line of debris was created. Timber from one shattered house battered down of the next. And the next.
Incredibly horrible. They found the city gone, they found 6,000 people gone. They didn't realize that at the time, although they knew how hard it would be. Most of them were simply trying to find their families, if anyone had survived, and then getting down to the business of
Probably better, yeah. It's actually a fairly gruesome tape. If anyone wants to watch the whole thing, you can borrow it from our department. But the point we wanted to make with that is that the only information they had to base a forecast on was really in real time. The chief of the Weather Service in Galveston looked outside and saw that it looked ominous. That ship report from Cuba was not nearly enough to give them any realization of what was coming. So this storm, that Galveston one, hit without warning, and that's the reason why the death toll was so high. Hurricane Andrew in 1992 was a significantly stronger storm, and it also hit a fairly populated area. It hit Florida, southern Florida. We'll look at the satellite track of it in just a minute, but we want to point out here the main tools, satellites being number one, that were available to forecasters in 1992. These satellites have the advantage that they can survey the whole world ocean. So whenever a storm is out there, even if it's in the dead center of the Atlantic, we know about it now. If these satellites had been available in 1900, we can probably assume that Galveston would have had very few deaths. People would have evacuated the island. We now have aircraft reconnaissance as well. Airplanes fly into these storms and measure the pressures and the winds and other variables. And when the storms approach the coast, we have radar to track them right down to the nearest couple of miles. Now, we're going to be looking at some satellite loops of Hurricane Andrew. But we wanted to review briefly how these satellites make their measurements. And this is a copy of one of the pages in your notes packet, I believe. Yeah, this is in the notes. What we're summarizing in that page in your notes are the types of wavelengths of radiation that satellites sense. The most common one and the one we relate to most easily is the visible. Satellites measure visible radiation so that they're seeing what we would see with our eyes. I mean, clouds and snow will look white, which is fine. But when it's nighttime, that doesn't work. So they use infrared radiation. When they measure the infrared radiation, they're really measuring the temperature of what is sending up the radiation to the satellite, and that emitter is either the ground or the tops of the clouds. It turns out that the coldest emitters, which will show up brightest in a satellite picture, are the highest cloud tops. They're highest up where it's cold. So these pictures, they're called infrared pictures, are really maps of the received infrared radiation, thermal emission, from things below the surface. There are also microwave sensors on some satellites which measure microwave radiation, and that radiation has the advantage that it passes through clouds. So you can actually map things like the surface temperature or some other surface properties without having to worry that clouds are blocking your view. So these three types of satellite pictures are available day in and day out to forecasters for the whole world. Now, for Hurricane Andrew, we have two sets of satellite footage, so you can see how this storm was tracked from its beginnings way out in the Atlantic. Now, this is number 3.
About 10 days before I got to Miami, about 3 days after that, we began to see the band features on the satellite pictures that pulled up to the depression was developing. And it actually came, the depression just on the 17th, which is a week before I got to Miami. And actually,
So there it is.
Later that same day. So what very real threat of the tropical hurricane because of Florida within the next 48 to 72 hours.
Okay, yeah, got it there. Now, we also have some computer animation of the track. You saw that storm when it was first detected out in the Atlantic moving towards Florida, but you didn't see it reach land. There are files of satellite images that can be tapped into for the home computer so that you can go back and reconstruct some of these satellite loops. Here is Andrew as it's approaching Florida. Florida is right there. You can see the storm. This is what forecasters would have been looking at the time they said there's a full-blown hurricane warning in effect. Okay, may want to loop it. Is it loop? Yeah, okay. Now these are infrared satellite pictures. They've artificially enhanced some of the brightnesses, which is why you see colors in there. The infrared sensor wouldn't be picking up colors necessarily. It shouldn't be picking up colors. But you can track this feature across Florida. The storm then went into the Gulf of Mexico. You can see the eye, it's that calm area in the middle. And the storm then moved up to Louisiana. But one of these pictures was coming back every 90 minutes or so from the satellites. So it was very clear just where the storm's center was. And by looking at 2 successive pictures, you can determine where the storm is moving, which direction it's going, and how fast. The storm finally went into Louisiana, right in there. But these satellite pictures are available to forecasters within about 30 minutes of the time the picture's taken. Thanks. So Andrew was definitely a well-tracked storm. There's not much you can do about a hurricane to reduce the damage, at least short term. So Andrew caused about $20 billion in property damage, but the death toll was only 20 to 30, compared with 6,000 from a weaker hurricane before we had these modern forecasting tools available to us. Now, in your notes, we also showed you a radar image, a radar picture of Andrew as it struck the coast. This is in black and white in your notes. This is a fairly impressive picture of the scale of the severe part of the storm. This is the coast of Florida. It's given by the white line. Miami is up right about here, the city of Miami. This area in here is the eye, where there's essentially no precipitation. What's happening in a storm like this is that there's a balance between two forces. The pressure gradient force, which is acting inwards, and the centrifugal force, as the air spins around. It's tending to keep the air from coming into the center. You get a strong balance, a balance between those two strong forces, which keeps the eye relatively clear. The centrifugal force is so strong that the air does not converge all the way in. But this area in red, which is the eye wall, was the area of major destruction. Winds of about 140 miles an hour were in this eye wall. The storm's eye wall, you can see from this radar picture, missed Miami by maybe 20 miles. The eye wall itself is only 15 or 20 miles wide, which means the width of the area that gets the most severe impacts was only maybe 40 miles wide. So we were somewhat fortunate that this didn't hit in the major urban area, but this is a fairly thickly settled area down south of Miami, and that's why the damage toll was as high as it was. But the people did have accurate warning to evacuate the coastal areas here and get safely inland to where they were at least away from the strongest winds and from the storm surge that came on shore. We have in your note packet some material on the storm surge, which I won't go through because we don't have time, but you might want to take a look at that because it takes you through some of the major factors that lead to damage from a hurricane. Okay, so we should probably move on now to the last of the main topics, which is the tornado topic. And in this case, we want to compare two tornado events and the warnings of it. First one is what is sometimes referred to as the most famous tornado in the history of the United States. It's called the Tri-State Tornado. This one occurred in 1925. Just had the anniversary of this one last week. So this was a March tornado that passed through 3 states. Illinois was the one that the tornado spent most of its time in. The path was over 200 miles long. The tornado was more than a half-mile wide for a good part of its path. So this was a major tornado. It came through at 60 or 70 miles an hour. The wind speeds they've estimated were in the upper 100, 180 to 200 mile an hour range. There were about 700 deaths from this tornado, almost all of them in southern Illinois. We'll look at the track in a second, but what we want to point out here is that once again, there were no warnings to speak of. We did not have radars back in the 1920s to track the storm that contained this tornado. We did have the telegraph and some telephone lines, but they were knocked down by the tornado. So those tools weren't much use in warning the people downstream of this tornado. What made it worse is there was no visible funnel because it was a very cloudy day and so much dust and debris was in the air. This storm tracked from Missouri through southern Illinois. And this is the track. I believe this is in the note folder. Is that in the notes? Maybe we didn't get it in there, but this is the track. The Mississippi River is right here. The storm in this part of the track was about 1/2 to 3/4 of a mile wide, and it came through in the afternoon, right when school was letting out. So a lot of the deaths were from children who were just getting out of school or still in school at the time it passed through. But most of the deaths and the most severe damage was in this area, where several towns were essentially obliterated. You'll see that in the short video segment we have. This video segment will also address the question of whether it really was one single funnel or not. Since we don't have any pictures, we don't have any radar records, we don't have any other data to speak of, most of the inferences have been done from the damage pattern. Okay, this would be the tri-state. Yeah, that one. Yeah, thanks.
One of the most long-standing puzzles in tornado involves the damage path of a tornado of 1925. The damage went on and on without a break for over 200 miles. Understanding of thunderstorms leads us to believe that such a long continuous but who does might have happened was filled with at about the same time as the tornado was passing through Heston. The tornado on the right was 4 miles to the north. And the tornado was stronger. The Heston tornado seen on the left were weaker. One would expect a tornado family to have a break. Two separate tornadoes was closer. As the Heston tornado began to roll out, it was absorbed into the circulation. This resulted in 2 separate tornadoes, with a continuous tornadic damage path. Could the tri-state have been such a phenomenon? And that was possible. Just 2 years later.
Now, that final sentence there, saying we'll never know, is really a summary of the data situation. We have very little information on that storm other than the damage pattern. But what we want to do now is contrast the situation with the present. It turns out that a few years ago, there was a major tornado outbreak in the Central Plains. This is sometimes referred to as the Andover, Kansas family of tornadoes. In this case, there were 50 tornadoes in approximately a 24-hour period. One of these tornadoes was even stronger in terms of wind speed than the tri-state. Now, that's a qualitative assessment. It's based on the types of damage that occurred on the field surveys after the storm passed through. But they've estimated that the winds in one of these 50 tornadoes, the one that hit Andover, were in the 250 to 300 mile an hour range. The track of this tornado, this very strong one, was 69 miles, not as long as the tri-state. On the other hand, we just heard the tri-state could have been more than one tornado, but we don't know. Several towns were hit by the tornadoes in this outbreak, but there were only about 20 deaths In fact, the sizes of the towns were somewhat larger in this case than the towns that were hit by the tri-state tornado in 1925. Only about 20 deaths. There was this F5 tornado, it's the highest ranking a tornado can have on severity, passed through a trailer park. And about 200 people had enough warning that they could go underground into a tornado shelter at that trailer park, and they survived. It was the Doppler radar that prompted the warnings on this storm. The people who were willing to react to the warnings had time to do so. There were some people who failed to heed the warnings, as your notes say, and they were the ones who, in some cases, were the fatalities. There is fairly good footage of several of the tornadoes in this outbreak. In fact, footage of several of segments of that 69-miler. But what we want to look at is the use of Doppler radar to detect the thunderstorms that contain tornadoes. And this is definitely in your notes, your note packet. We said earlier that radars have been in use since the 1950s for weather purposes. The so-called Doppler radars have been in use for about 10 years. And we want to go through the physical principle behind the use of Doppler radar. A radar really is a beam of microwave radiation that is transmitted, reflected off precipitation or some other material in the atmosphere, and it's bounced back to the receiver that's usually at the same spot that the beam was transmitted from. The beams are about 1 centimeter in wavelength, not too different from what's in your microwave ovens. The old network was not a Doppler radar network. They were just plain old radars that measured precipitation when it was out there, but they could not tell you anything about winds. We want to go through the use of these for winds, and that's why we've sketched these two diagrams at the bottom. What you're taking advantage of with the Doppler radar is the Doppler effect that you run into in physics. The transmitted beam has a certain frequency. So this is your transmitter. If there's a reflector, say a thunderstorm out there, in which the air is moving, and that air is moving towards the transmitter, that means that beams sent out at a later time, pulses sent out at a later time, have less distance to travel out and back to return to the receiver. So the effect is that you're going to receive these return pulses at a higher frequency than you're sending them out. It's the same effect you have when a train is approaching you with its horn sounding. You get a higher pitch or a higher frequency as the train is coming towards you. In that case, it's not a reflector, it's an emitter that's coming towards you, but it's the same principle in terms of frequencies. If the reflector is moving away from you, each successive wave has to travel a little farther out and back, so the frequency is lower. So if you receive a low frequency in your return signal, you can assume that the target is moving away from you. In the case of the train, the pitch goes lower when the train passes you and goes down the track away from you. Doppler radar, well, we summarized what these radars measure. One of your figures. The first three items here are measured by both types of radar, non-Doppler and Doppler. The distance to precipitation, the altitude of the precipitation, and the intensity of the precipitation. It's the Doppler radar that measures the winds. It's really measuring the motion of the raindrops that are being carried by the winds. But it's this wind information that turns out to be very useful for tornado detection. We'll show one example of a regular radar image that has been processed to estimate how much precipitation actually fell. This example is from the Mississippi flood event of 1993, but it's a radar-deduced precipitation map where they've summarized or summed up all the precipitation totals over a period of about 24 hours and mapped it. And the radar summary is saying that there were precipitation amounts up around 6 and 7 inches in this small area. This St. Louis is right over here, so this is Missouri. This map gives you an idea of the detail you can get in these radar maps. But this does not, again, get at the wind issue. What we have now, and what we'll look at in a couple other examples, is a Doppler radar return of the winds. Now, what these Doppler radars are measuring when they measure the winds is the component of the wind along a radial line extending outwards from the radar, from the transmitter. All it can tell you is whether the air is moving away from your line of sight, out past you, or coming back. It can't give you the lateral or the transverse component. In this particular case, it happens to be the same radar, the one down near St. Louis, the radar site is down here. That color scale gives you the wind component towards or away from the radar. The positives are winds away from the radar. The negative are the greens, the negatives are the winds towards the radar, and they're green. But what you see in this area, which is a thunderstorm area, is a pair of wind indications that are in opposite directions. The air here is moving away from the radar. The air here is moving towards the radar. That is consistent with rotation. So if the pattern here is counterclockwise rotation in that area, you would get a radial velocity field like this one that matches up with the return in this example. This was a tornadic thunderstorm. This is not showing you the actual tornado rotation, but it's the rotation in what they call a mesocyclone that the tornado descends from. And these mesocyclones that rotate are reliable enough indicators of tornadoes that they now issue tornado warnings when they detect this type of signature, this type of velocity pattern in a Doppler radar return. And it was an image very similar to this one that led them to issue some of the warnings in that Andover, Kansas tornado event. Now, one last item before we look at some real-time images. You may want to track down a radar map since we're about out of time. When you get these rotating thunderstorms, if you ignore the winds for a second and just reason what the radar return should look like, the precipitation pattern, there's a wraparound effect. This is a view of a rotating thunderstorm from above. And what happens is that in the area where the strongest updraft occurs, the air is going up so fast that the rain or the ice particles can't fall. They're carried upwards and outwards. So you get a clear area in here, but the precipitation wraps around that clear area, which is, the clear area is called a vault. And that forms something that looks like a hook. And before Doppler radar was available, that hook echo was sometimes used as an indication of a tornado. This is an example of a radar return from a thunderstorm that produced a hook echo. This is Colorado and Kansas. Right out here is one of those storms that has a radar return like a little hook. So there's your clear area in the middle and the hook. So even if you did not have Doppler radar and saw a return like this one, you could issue a tornado warning. The problem is that this hook appearance is not as reliable an indicator of a tornado as the wind signature indicating the rotation is. Now what we have here that we'll finish with are some examples of the type of radar information you can get in real time. Just in the last year or two, these Doppler radar fields from sites all around the country have become available on the internet. So we're tapped into some weather data here, and Bill has chosen the is that the St. Louis radar? You might have noticed he had a whole list of cities to choose from. You can click on the one you want and see what's going on in terms of precipitation. This is the return from a radar around St. Louis, and it's very current. Did it give the exact time? 15. Okay, that's less than an hour old. see where we are. The Mississippi River. You see where the Mississippi is? Okay, that's the Mississippi River. So Illinois is over here, and this is Missouri. St. Louis is right here. Yeah, St. Louis is right there. There are some thunderstorms right now moving in towards St. Louis. And it's a fairly respectable area. The yellows are the heavier precipitation areas. And if you have, we've followed those this morning. They've moved across Missouri and are just entering Illinois now. So we might want to keep an eye out on the sky to see if these things actually make it towards us. I think we're somewhere off the map, or is that Champaign County? I think we're off the map. Yeah. There's the northern border of Missouri. You think that's us? Yes. Okay, that would be us. Yeah, that's the northern border of Missouri. So this area is moving eastwards. We may be affected by it later on. There are none of the highest intensity levels, which would be red in this particular pattern. So these are, in all likelihood, not severe thunderstorms. We don't see any hook echoes, but it is clear that something's moving in. At the end of your note packet, we did give you some access information for these different types of weather data. So if you have a computer terminal with access to the internet, these things are retrievable, and you can get radar images from anywhere around the country that are less than an hour old. Okay, did you have any others you wanted to look at? Okay, one last, yeah, we'll take a look at one last item from the network, and then we'll be finished. We'll take a look at a forecast that you can also get off the internet of weather conditions for the next, I guess it'll be 48 hours ahead. We're going to look at a forecast of the sea level pressures for Sunday. There's a potentially very interesting weather situation developing as far as severe weather goes. Bill has put up here a plot of the sea level pressures in terms of isobars. These black lines are isobars. That was produced by a computer model from the European Center. This model is run over in England, but it turns out to be a very good one, probably the best in the world. It's a forecast of the sea level pressures for tomorrow. And what is showing up here is a very strong low pressure center with an airflow that's counterclockwise around it, but the pattern would be bringing in Gulf of Mexico air. At this time of year, when you get that combination of Gulf of Mexico air over us, strong low to the west, the stage is set for severe weather. So even though we don't have severe thunderstorms in progress now, tomorrow is looking very much like a severe weather day for the area, at least south and west of here, perhaps closer to us tomorrow night. So if you do want to monitor the thunderstorms with that internet, this next 24-hour period would be a very good one. Okay, thanks. Here's the summary that's in the note, and it's just a subjective look at some likely happenings in the near future. The tendency you might have noticed in these comparisons is that we're getting more damage from severe weather events because there's more to be damaged, but definitely lower death totals. Those trends are likely to continue. We're likely to see data from some of these newer technologies fed into the computer models to sort of feed on the advantages of both and improve weather forecasts even more. The public is becoming more weather-wise, partly because we have access to these types of weather data. We also have the Weather Channel on full 24 hours a day. On a more ominous note, it is likely, it's almost certain that sooner or later, if we wait long enough, there will be a major hurricane or a major tornado in a large urban area. We haven't really had any of those for the last 20 or 30 years. I'd keep an eye out for this, at least in our lifetimes, and that could rescale the measures of damage that we've been getting from these severe weather events. The final item is that if greenhouse warming indeed sets in, there have been some studies done to suggest that hurricanes may become stronger, since more moisture will be input to the atmosphere. tornadoes could become more numerous, and there could be a tendency that is already showing up in the data for more heavy rain events, more flood events. So we may not have seen the worst of the severe weather for the decade that we happen to be living in. If greenhouse warming occurs, things could indeed get a little worse, which means that some of the topics we looked at today may become a little more prominent in the news. But time will tell on that. So I'll stop and take questions.